Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome to the Deep Dive. Today, we're taking a journey into the fundamental systems that truly keep an aircraft flying safely and smoothly.
That sounds great. These are the core components, really.
Our mission for this deep dive, specifically for you, our student pilot listener, is to give you a clear shortcut to understanding the critical components of your training aircraft.
Yeah, we want to get past just naming parts.
We're talking fuel, electrical, hydraulic, and landing gear systems. We'll unpack the essential knowledge, maybe bust a few myths.
And really focus on the practical side, what you need to know in the cockpit for pre-flight.
And zero in on what really matters for your pre-flight checks and overall operational safety as you work towards that private pilot certificate.
Exactly. Understanding these basics isn't just for the written test. It's fundamental for confident flying, knowing what to look for, and frankly, how to react if things don't go as planned.
Okay, let's kick things off then. With the fuel system, you could say it's literally the lifeblood of your aircraft. At its core, what's its number one job?
Well, simply put, yet absolutely critical. It's designed to deliver a continuous, clean supply of fuel from the tanks right to the engine.
Under all conditions, right.
Under all conditions of flight, any power setting. Reliability is key.
And for most small aircraft, the kind student pilots fly, we typically see two main approaches.
Precisely. First, you've got the gravity feed system. Super common in high-wing planes. Think like a Cessna 172.
Because the tanks are up high.
Exactly. The tanks are in the wings, higher than the carburetor, so gravity just does the work. Simple.
But then you have low-wing planes.
Right. And if you're in a low-wing aircraft, the tanks are below the engine level. Gravity isn't going to cut it there.
So that's where you need pumps.
That's where you get a fuel pump system. It actively pushes the fuel uphill to the engine.
And here's a key point, I think. For safety, it's not usually just one pump doing all the work in those systems.
You got it. Most fuel pump systems actually have two. A primary pump, which is driven mechanically by the engine itself, and then an electrically driven auxiliary pump. You probably know it as the boost pump.
Right, the one you flip on with a switch.
That's the one.
Yeah.
It's absolutely vital for starting the engine, before the engine-driven pump is really spinning up.
And it's a backup, too.
A critical backup. If your main engine-driven pump fails in flight, that electric boost pump is your lifeline. You turn it on, and it keeps the fuel flowing.
Speaking of starting, sometimes you hear about a fuel primer. What's its role?
The primer. It's there to help get the engine going, especially on a cold day.
How does it do that?
It basically draws a small amount of fuel directly from the tanks and vaporizes it right into the cylinders, kind of bypassing the carburetor initially.
So it gives a richer mixture for starting.
Exactly. When the engine's cold, the carburetor might not vaporize fuel efficiently enough on its own. The primer gives it that extra kick needed for an easy start.
Is there a safety gotcha with the primer? Something student pilots should really watch out for?
Yes, definitely. It's absolutely critical to make sure that primer knob is pushed in and locked in place after you use it.
Why is that?
Well, if it vibrates out, even just a little bit during flight, it can allow extra fuel to seep into the engine continuously.
Causing problems.
Oh, yeah. An excessively rich mixture. It can lead to fouled spark plugs, rough running, maybe even an engine stoppage. It's a small detail, but checking that lock is a vital pre-flight and post-start habit. Always double-check it.
Good tip. Let's move to the fuel tanks themselves. They're not just simple containers, are they? There's some smart engineering there.
They really aren't. Typically, they're in the wings, obviously with filler openings and caps, but crucially, they are vented to the outside atmosphere.
Why is venting so important?
Two reasons. As fuel gets used up, air needs to replace it to prevent a vacuum from forming, which could stop fuel flow. Also, temperature changes cause fuel and air inside to expand and contract. The vent allows pressure equalization.
And they often have an overflow, too.
Yes, an overflow drain sometimes is part of the vent system. This lets fuel expand safely on hot days without stressing the tank structure.
So if you see a little drip under the wing on a hot day after filling up?
Don't panic immediately.
Yeah.
It might just be normal expansion through the overflow. Of course, investigate any persistent leak, but a small drip on a hot ramp can be normal.
Now, a really big one for student pilots.
Hey.
Fuel gauges. How much faith should we put in them?
The golden rule of fuel management. Never, ever depend solely on your fuel gauges. It's a hard-learned lesson sometimes.
Why not? Aren't they required to be accurate?
Well, here's the thing. Aircraft certification rules only strictly require them to be accurate when they read empty.
Only when empty. Seriously.
Seriously. Any other reading, whether it's full, half, quarter,
Huh.
treat it as an approximation, a rough guide at best.
So the absolute essential takeaway for a student pilot.
Always physically look into each fuel tank during your pre-flight. Use a dipstick if necessary, or just visually check the level. Then compare what you see with what the gauge says. That visual check is non-negotiable. It's the only way to be sure.
Got it. And if you're flying an aircraft with a fuel pump, you'll also have a fuel pressure gauge.
Correct. It shows you the pressure in the fuel lines downstream of the pump.
And there's a normal range.
Yes. Your aircraft's AFMPOH, that's the Aircraft Flight Manual or Pilot's Operating Handbook, will specify the normal operating pressure. Usually it's marked clearly with a green arc right on the gauge face.
Okay, let's talk about the fuel selector valve. Seems simple, but maybe there are nuances.
It does seem simple. Most common selectors have positions like left, right, both, and of course off.
Left or right just draws from that tank.
Yep. And both typically draws fuel from both wing tanks simultaneously.
Why would you choose left or right instead of both?
On longer flights, you might select one tank for a period, then switch to the other. This helps you manage and balance the fuel load between the wings, which is important for maintaining aircraft stability and control.
So what's the big picture here for a pilot managing fuel in flight using the selector?
Vigilance. You must monitor your fuel consumption carefully. Running a tank completely dry is a bad idea for several reasons.
Obviously, the engine stops.
Well, yes, that's the most obvious. But even before that, it can cause an unbalanced fuel load, making the plane harder to handle.
And there's another risk.
Yes. Crucially, if you run a tank totally dry, air can get sucked into the fuel system. This can lead to something called vapor lock, especially in fuel-injected engines where the fuel lines get hot.
Making it hard to restart.
Extremely difficult, sometimes impossible in the air. Air in the lines disrupts fuel flow, so switch tanks before one runs dry. Also, always check for any fuel placards near the selector. They might have important limitations like use both for takeoffs and landings.
Good points. Now, keeping the fuel clean, fuel strainers, sumps, and drains. What's their role?
These are all about preventing contamination from reaching the engine. Think of them as the fuel system's filters and collection points.
How do they work?
Fuel passes through a strainer, which is like a fine screen, to catch solid particles. Any heavier contaminants, especially water and sediment, tend to settle down into a sump.
And a sump is just
A low point designed into the system in the tanks at the fuel strainer, specifically to collect this gunk.
And this leads directly to one of the most critical pre-flight checks for any student pilot, right?
Absolutely. This is 100% non-negotiable. During every pre-flight, you must drain fuel samples from the main strainer drain and from each individual tank sump.
Into a clear container.
Into a transparent container, yes. Then you hold it up and look closely. You're checking primarily for water and any sediment or other contaminants.
What does water look like in AVGAS?
Water is heavier than fuel and doesn't mix, so it'll appear as clear, distinct droplets or globules sitting at the very bottom of your sample cup. Sometimes, if it's finally dispersed, it might just make the fuel look cloudy or hazy.
Why is water so incredibly dangerous?
Two big reasons depending on temperature. In cold weather, that water can freeze solid, potentially blocking fuel lines, filters, you name it, starves the engine of fuel.
And in warm weather?
In warmer conditions, the water might not freeze, but it can still flow along with the fuel right into the carburetor or fuel injection system. Water doesn't burn, so engine stops.
So if you find any water,
You must keep draining samples from that sump point until absolutely no trace of water remains, not a single droplet. Never ever take off if you find water or any visible contaminants in your fuel samples, period.
Okay, switching gears slightly. Fuel grades. AVGAS isn't just generic gasoline.
Oh, far from it. Aviation gasoline, AVGAS, is specifically formulated for aircraft piston engines. It's identified by its octane or performance number.
Which tells you.
It indicates its anti-knock value, basically, how much pressure it can withstand in the cylinder before detonating or exploding prematurely, instead of burning smoothly. Higher numbers mean more resistance needed for higher compression engines.
Here's a crucial safety point. What if the correct grade for your aircraft isn't available?
This is critical. Always use the next higher available grade. Never, ever use a lower grade.
Why is using a lower grade so bad?
Using a lower octane fuel than specified can lead to detonation, that premature explosion in the cylinders. This causes extreme temperatures and pressures, which can quickly lead to severe engine damage, overheating, and power loss.
So how do you, as a student pilot, make absolutely sure you're getting the right fuel?
Check multiple places. The correct grade is always listed in your AFM-POH. There should also be placards on the flight deck near the fuel gauges or selector, and critically, right next to the fuel filler caps on the wings.
And the fuels have different colors.
Yes, they're dyed for easy identification. For example, AVGAS 100LL, low lead, which is very common, is blue. AVGAS 100, higher lead, less common now, was green. AVGAS 80 was red. Knowing the color helps confirm you're getting the right stuff. Jet fuel, by the way, is typically straw-colored or clear and smells like kerosene, totally different.
And the big warning about car gas.
Absolutely critical. Never use automobile gasoline in an aircraft engine unless the aircraft has a specific supplemental type certificate, an STC, from the FAA explicitly allowing it. Standard car gas lacks the quality control, additives, and detonation resistance needed for aviation use. It's just not worth the risk.
You mentioned fuel contamination earlier. It's a leading cause of engine problems. What are the common ways fuel gets contaminated?
Well, number one is probably an inadequate pre-flight inspection by the pilot not draining sumps properly or enough.
Okay, what else?
Servicing the aircraft with improperly filtered fuel, maybe from questionable sources like small tanks or drums. Another big one is storing the aircraft with tanks only partially full.
Why is that bad?
Empty space in the tank allows air, and the moisture in that air, to condense on the tank walls as temperatures fluctuate. Water builds up. And of course, just a lack of proper maintenance on the fuel system itself can be a factor.
So what's your best advice for a student pilot to actively prevent contamination?
First, be thorough with those sump drains. Drain enough fuel until you are absolutely certain you're getting fuel directly from the tank, not just what was sitting in the fuel line or the sump itself. If you find contaminants, keep draining until it's perfectly clear.
And about storage?
Always try to fill the fuel tanks completely after each flight, or at least at the end of your flying day. This minimizes the airspace inside the tank, reducing the potential for condensation to form.
Avoid refueling from cans?
If you possibly can, yes. Refueling from portable cans or drums should be a last resort. Their filtration systems, if they even have them, are often inadequate for aviation standards. Stick to reputable FBOs with proper fueling equipment whenever possible.
I've heard some old tales about using a chamois skin to filter fuel in emergencies. Is that a valid technique?
The chamois filter story, it comes up. But frankly, it's highly hazardous and generally ineffective.
Why hazardous?
A worn-out chamois doesn't filter water well. Even a good one, if it gets wet, stops filtering water. Plus, many modern chamois cloths aren't real chamois and don't filter water at all. And using one can introduce static electricity risks if not done perfectly. It's really an outdated and dangerous practice. Don't rely on it.
Good to know. Let's touch on fuel system icing. How does ice form in the fuel?
Ice forms from water suspended in the fuel. You can have free water, which settles out. You can drain from sumps. But there's also entrained water, tiny droplets suspended within the fuel itself, sometimes making it look hazy.
And that's the dangerous part for icing.
Yes, because that entrained water can freeze as the fuel cools, potentially blocking fuel screens, filters, strainers, or even narrow passages in the fuel lines or carburetor jets. It can also contribute to carburetor icing.
How do we prevent this, besides draining water?
Some aircraft are approved to use fuel system anti-icing additives, like Prist. But the concentration has to be right. And here's the really crucial point. Anti-icing additives are never a substitute for using carburetor heat when conditions warrant.
Carb heat is still primary.
Absolutely.
Yeah.
Carb heat is your main defense against carburetor icing. Always follow the operating instructions in your AFM-POH for using carb heat, especially when you suspect icing conditions.
Okay, final fuel topic. Refueling procedures and the danger of static electricity. This seems really important.
It is absolutely critical for safety. Static electricity can build up just from air flowing over the aircraft surface or even from the fuel flowing through the hose and nozzle.
Even clothing can be an issue.
Yes, things like nylon, Dacron, or wool clothing are particularly prone to building up a static charge on a person. And a tiny spark is all it takes to ignite fuel fumes.
So what's the mandatory procedure?
To prevent a spark, you must always attach a grounding wire from the fuel source or truck to the aircraft before you even remove the fuel cap. This equalizes the electrical potential. Then, you need to bond the refueling nozzle itself directly to the aircraft structure, like the filler port, and keep it bonded throughout the entire refueling process. This prevents a spark between the nozzle and the aircraft. If using a fuel truck, the truck should be grounded first as well.
What if you're in a rare situation fueling from drums or cans? What's the sequence?
It's a specific sequence. First, connect the drum to a proper ground point. Second, connect that same ground point to the aircraft. Third, connect the drum itself to the aircraft or the nozzle to the aircraft. Only then do you remove the fuel cap.
And disconnect in reverse.
Disconnect in the exact reverse order. And definitely never use plastic buckets or other non-conductive containers for refueling. They can't dissipate static charge and are incredibly dangerous.
Wow, lots to consider just with fuel. Okay, let's pivot to keeping warm, heating systems. What should a student pilot know?
Well, the first thing is that heating systems vary quite a bit. So the crucial takeaway is always reference the specific aircraft operator's manual, AFMPOH, for your aircraft's heating system. Operating procedures and risks differ.
What's most common in basic trainers?
For most light piston engine trainers, you'll typically find exhaust heating systems. They're relatively simple.
How do they work?
They use a shroud or heat exchanger around the engine's hot exhaust muffler. Fresh outside air is ducted through this shroud, gets heated up by the muffler, and then is directed into the cabin when you open the cabin heat control.
Simple, but there's a major safety risk associated with them, isn't there?
There absolutely is, and it's a potentially lethal one. Carbon monoxide poisoning.
How does that happen?
If there's a crack, leak, or defect anywhere in that exhaust muffler or manifold inside the heat shroud, the hot exhaust gases, which contain colorless, odorless carbon monoxide, CO, can mix directly with the heated cabin air.
And CO is deadly.
Highly dangerous. It reduces the blood's ability to carry oxygen. This risk highlights why inspecting the exhaust system thoroughly during pre-flight and maintenance is critical. Look for cracks, leaks, or excessive wear. It's also why CO detectors are highly recommended, if not required, in aircraft cabins.
Are there other types of heaters student pilots might encounter later?
Sure. Some slightly larger or more complex small aircraft might have fuel-fired heaters. These are like small self-contained furnaces that burn aircraft fuel.
Do they have similar risks?
They can, yes.
Oh.
They burn fuel in the combustion chamber, and air is blown over that chamber into the cabin. If not properly maintained or vented, combustion byproducts, which can include some carbon monoxide, could potentially leak into the cabin air. Proper maintenance is key.
And then much larger aircraft.
Turbine aircraft often use bleed air heating systems. They take super hot air bled from the engine's compressor section, mix it with cooler ambient air to get the right temperature, and duct that into the cabin. These are complex systems with many safety features.
Okay, let's switch gears and talk electricity, the electrical system. What powers everything in a typical trainer?
Most small training aircraft run on either a 14-volt or a 28-volt direct current DC electrical system.
And what are the key players in that system?
Well, you've got a source of power, which is usually an alternator, sometimes an older generator. You have a battery for starting and backup, a master switch, often split into battery and alternator sides,
What else?
a bus bar to distribute power, fuses or circuit breakers for protection, a voltage regulator to keep things stable, and then gauges like an ammeter or load meter to monitor the system, plus all the wiring connecting everything.
You mentioned alternators and generators. What's the main difference for a pilot?
Both do the same basic job: generate electrical current to power the aircraft systems and recharge the battery. However, alternators are generally preferred in modern aircraft.
Why is that?
The big advantage is that alternators produce sufficient current even at lower engine speeds, like during taxi or idle. Generators often don't produce enough power until the engine is running at higher RPMs, meaning the battery gets drained more during ground operations. Alternators also tend to be lighter and more reliable.
So the battery is really just for starting in emergencies.
Pretty much. It provides the initial power to crank the engine, and it acts as a limited emergency power source if the alternator or generator fails in flight.
Some planes have a plug for external power.
Yes, you might see a receptacle for an external ground power unit, or GPU. Very useful, especially for cold weather starts or maintenance, as it provides electrical power without draining the aircraft battery. Always follow the manufacturer's procedures when using one.
When you flip that big red master switch on, what actually happens? What gets power?
Turning the master switch on connects the battery, and later the alternator, to the main electrical bus. This provides power to essentially all the electrical circuits in the aircraft, except for the engine ignition system, which is usually self-contained on magnetos.
So lights, radios.
Yep. Position lights, anti-collision lights, landing and taxi lights, cabin lights, instrument lights, all your radio and navigation equipment, the turn coordinator, fuel gauges, electric fuel pump if you have one, stall warning system, pitot heat, and of course the starter motor circuit. It energizes the whole ship, electrically speaking.
And sometimes that master switch is split, or there's a separate alternator switch.
Correct. Often it's a split rocker switch, one side for the battery, the other for the alternator or generator. Some aircraft might have a completely separate alternator switch.
What's the purpose of being able to switch the alternator off separately?
It's primarily for managing an electrical problem. If the alternator fails or starts acting erratically, you can turn its half of the switch off. This isolates it from the system and places the entire electrical load purely on the battery.
And if that happens, what should a pilot do?
If you lose your alternator, the immediate action is load shedding. That means turning off all non-essential electrical equipment, extra lights, secondary radios, maybe even pitot heat if not in icing, to conserve whatever battery power you have left. You need to save that power for essential instruments and maybe one radio comm for landing.
Okay. You mentioned a bus bar. What exactly is that?
Think of a bus bar as a central distribution point.
Yeah.
It's basically a solid metal strip or bar inside the panel where the main power wire connects, and then all the individual circuits for radios, lights, etc. branch off from it. It simplifies wiring and provides a common connection point for everything that needs power.
And protecting those circuits are fuses and circuit breakers. Big difference.
Huge difference in how you handle them. Both protect circuits from overloads, too much current flowing through. A fuse contains a thin wire that melts and breaks the circuit if the current gets too high. Once it blows, it's done. You have to replace it.
So carry spares.
Absolutely. Always carry spare fuses of the proper amperage ratings for your aircraft. A circuit breaker, on the other hand, is like a resettable switch. If it detects an overload, it pops out, breaking the circuit.
Can you just push it back in?
Generally, you can try resetting a popped circuit breaker once after letting it cool for a moment. If it pops again immediately, there's a persistent problem in that circuit, and you should leave it out and have it investigated on the ground. Don't keep resetting it. Both fuses and breakers are labeled to show which circuit they protect and their amperage limit.
How do we keep an eye on the electrical system's health in flight?
You'll typically have either an ammeter or a load meter. They tell slightly different stories.
What does the ammeter show?
An ammeter usually measures the amount of current flowing to or from the battery. A positive indication, plus side, means the alternator is working fine and is recharging the battery. A negative indication, minus side, means the battery is discharging. More power is being drawn than the alternator is supplying.
So a big negative reading means?
A large continuous negative reading strongly suggests an alternator failure. Conversely, a full-scale positive reading might indicate a problem with the voltage regulator, causing overcharging. Always consult your AFM/POH for specifics on interpreting your ammeter.
And a load meter, how is it different?
A load meter shows the total load being placed on the alternator, or generator. It's usually calibrated in percentage of the alternator's total capacity. So as you turn on radios, lights, etc., you'll see the load percentage increase. It directly shows how hard the alternator is working, rather than focusing on battery charging status.
Which is more common now.
Load meters are becoming more common in newer aircraft designs. Again, know how to read whichever system your aircraft has. Some planes might just have a warning light for an alternator failure instead of a gauge. Check your POH.
And lastly, for electrical, the voltage regulator, its job.
The voltage regulator is like the system's thermostat. It automatically controls the output of the alternator or generator to maintain a constant predetermined voltage for the electrical system, like 14 or 28 volts. It also prevents the alternator from overcharging the battery. It ensures the output voltage is just slightly higher than the battery voltage so the battery stays charged.
Okay, system number 4. Hydraulic systems. What do they typically do in small planes? Not flight controls, usually.
Not usually primary flight controls in small trainers, no. In most small aircraft, hydraulics are commonly used to operate things like the wheel brakes, retractable landing gear, and sometimes the mechanism for constant speed propellers.
So things that need significant force.
Exactly. Hydraulics multiply force effectively. In larger, more complex aircraft, their role extends significantly, operating flaps, spoilers, flight controls, thrust reversers, you name it.
So what are the basic components of a simple hydraulic system, say, for brakes or landing gear?
A basic system needs a few key parts. You need a reservoir to hold the hydraulic fluid, a pump to create pressure. This could be a simple hand pump, an electric pump, or one driven by the engine.
What else?
You need a filter to keep the fluid clean, crucial for reliability. A selector valve to direct the pressurized fluid where it needs to go, like gear up or gear down. A relief valve as a safety device to prevent overpressurization. And finally, the actuator or servo that actually does the work.
A servo? What's that?
A servo, or actuator, is typically a cylinder with a piston inside. Hydraulic fluid pushes on the piston, converting fluid pressure into linear mechanical force or motion. That motion is then used to move something, like retracting a gear leg or applying brake pressure.
Can they push both ways?
Yes. They can be single-acting, where pressure moves them one way and a spring returns them, or double-acting, where hydraulic pressure is used to move them in both directions, like for both extending and retracting landing gear. A selector valve is needed to reverse the fluid flow for double-acting servos.
And the relief valve is just a safety backup.
Purely safety. If pressure in the system somehow builds up too high, maybe due to a blockage or pump issue, the relief valve provides an escape path for the fluid, preventing lines from bursting or components from failing.
What kind of fluid do these systems use? Is it special?
Yes, it's specific hydraulic fluid. Most small aircraft use a mineral-based hydraulic fluid, often designated MILH 5606. It's typically dyed red for identification.
What are its properties?
It needs good lubricating qualities, needs to resist foaming and corrosion, be chemically stable, and critically maintain a relatively stable viscosity across a wide range of operating temperatures.
And using the wrong type.
Extremely bad idea. Crucially, always use the exact type of hydraulic fluid specified by the aircraft manufacturer in the AFMPOH or maintenance manual. Mixing fluid types or using the wrong type can cause seals to swell or shrink, leading to leaks and potentially catastrophic system failure. Don't guess.
Got it. Last major system for today. Landing gear. More than just wheels, right?
Absolutely. While wheels are the most common way aircraft interact with the ground, they can also have floats for water operations or skis for snow. But fundamentally, the landing gear is the aircraft's principal support when it's not flying.
And for typical land planes that student pilots fly, there are two main configurations.
That's right. You have conventional landing gear, which many people call tailwheel or tail dragger aircraft. And then you have tricycle gear.
Describe conventional gear first.
Conventional gear has two main wheels positioned forward, usually slightly ahead of the aircraft's center of gravity, CG, and then a third, much smaller wheel at the very tail.
And tricycle gear.
Tricycle gear, which is what the vast majority of modern trainers have, features a steerable or castering nose wheel positioned under the front of the aircraft, and then the two main wheels located further aft, typically under the wings or fuselage behind the CG.
Now, here's a really important distinction for theater pilots. Why is tricycle gear so much more common for training? What are its advantages?
There are three really significant advantages to tricycle gear, especially for learning.
Okay, number one.
One, you can apply much more forceful braking during landings, even at higher speeds, without the inherent risk of the aircraft nosing over onto its propeller. The geometry makes it stable under braking.
Makes sense. Number two.
Two, forward visibility. During takeoff, landing, and especially taxiing, the pilot has a much better unobstructed view straight ahead over the nose in a tricycle gear airplane.
That's huge for situational awareness.
Absolutely. And number three, this is arguably the biggest one for ground handling. Tricycle gear significantly helps prevent ground looping.
Explain ground looping.
A ground loop is a violent, uncontrolled turn or swerve on the ground, often happening during the landing, rollout, or takeoff run in tailwheel aircraft.
Why does tricycle gear prevent it?
Because in a tricycle gear airplane, the aircraft's center of gravity is located forward of the main landing wheels. This creates inherent directional stability. If the plane starts to yaw slightly, the CG's momentum tends to pull it back straight. It wants to keep going straight.
And those nose wheels themselves, they can be steerable or castering?
Correct. Steerable nose wheels are linked mechanically to the rudder pedals, so you steer on the ground primarily using your feet, just like you control yaw in the air. Very intuitive.
And castering.
Castering nose wheels swivel freely, kind of like the front wheels on a shopping cart. With these, steering on the ground requires using the rudder for aerodynamic effect at higher speeds, combined with skillful, independent application of the main wheel brake's differential braking to make turns at lower speeds. It takes a bit more practice.
So, given all the advantages of tricycle gear, what's the situation with tailwheel landing gear? Why do people still fly them, and why are they harder?
Tailwheel aircraft definitely have their place. They often allow for larger propeller diameters, giving better prop clearance, which is great for operating off rough or unimproved fields. Some pilots just prefer their handling characteristics in the air as well.
But the ground handling is the challenge.
That's the main difficulty, yes. The big disadvantage is that the center of gravity is located behind the main landing gear wheels.
Making it unstable?
Directionally unstable on the ground, yes. If a tailwheel aircraft starts to swerve or yaw during takeoff or landing, the CG's momentum actually tries to pull the tail around the main wheels, potentially tightening the turn into that dreaded ground loop. It requires constant, precise rudder inputs from the pilot to keep it straight.
And visibility.
Forward visibility is also significantly diminished when the tailwheel is on or near the ground because the nose points up at a high angle. Pilots often have to make S-turns while taxiing just to see where they're going.
So specific training is needed.
Absolutely. Operating a tailwheel airplane safely requires specific training and endorsement. It's a different skill set for ground handling.
And briefly, fixed versus retractable gear.
Fixed landing gear always remains extended. It's simple, relatively light, and requires less maintenance. Very common on trainers.
And retractable.
Retractable landing gear is designed to fold up into the aircraft's structure, wings, or fuselage during cruising flight. This cleans up the aerodynamics significantly, reducing drag and allowing for higher cruise speeds and better fuel efficiency. But it adds weight, complexity, and maintenance requirements.
And one last bit. Brakes. Where are they and how do they work?
Brakes are located on the main wheels, only not usually on the nose wheel or tail wheel. They're typically operated either by a hand control lever or, more commonly, by foot pedals. Often these are toe pedals on top of the rudder pedals or sometimes heel pedals.
And you can brake independently.
Yes, a key feature with foot pedal brakes is that the left and right main wheel brakes operate independently. This allows for differential braking, applying more brake pressure to one side than the other.
Why is that useful?
It's crucial for steering during ground operations, especially for tight turns at low speeds. It supplements the nose wheel or tail wheel steering authority significantly. It's a fundamental skill for taxiing.
Wow. What an incredible deep dive into, well, the guts of an aircraft. We've covered so much, from fuel flow to keeping warm, electrical power, hydraulics, and how you stay safe on the ground.
It's a lot. But the big picture here, especially for you as a student pilot starting out, is that really understanding these core systems isn't just academic book knowledge.
It's practical safety.
It directly impacts your safety and your proficiency, absolutely. From visually checking your fuel levels, knowing why that's critical, to understanding exactly why your tricycle gear trainer behaves differently on the ground than a tail dragger. This knowledge equips you for confident, informed decision-making.
And knowing where to find the specifics.
Always go back to your aircraft-specific AFM or POH. That's the final authority for your airplane.
Absolutely. So as our student pilot listeners head out for their next lesson or flight, what's a final thought you want them to chew on?
Maybe consider this. Think about how seemingly minor details, things we've talked about, like the type of hydraulic fluid used or the exact placement of an aircraft's center of gravity relative to its landing gear, or that little vent on the fuel cap, how these details have such profound impacts.
Impacts on maintenance, procedures.
Operational procedures, and ultimately flight safety. So the question to mull over is, how many other minor details in aviation, maybe things you haven't even focused on yet, hold similar critical importance, just waiting for you to uncover them and truly understand their silent, vital role in keeping you safe?
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.